Hello and welcome to this lecture on human perception in immersive environments. At the end of today's lecture, you will be able to explain what is known as the perception action loop and its relevance to immersive systems. You will be able to describe the sensory pathways involved in XR experiences. You will be able to differentiate between monocular and binocular depth cues. You will be able to explain how visual displays and tracking systems support stable perception in XR, and you will be able to discuss the role of multisensory integration in creating presence and immersion. Let us start with an overview of human perception. One can think of perception as interpretation and not just sensing. It is not just sensing the world around us, but about making some interpretation about it, getting some meaning about what we are sensing in the world, and that requires multisensory integration. The way humans perceive is what can be thought of as an perception action loop. In this perception action loop, there is an iterative cycle of perceiving the environment and taking actions based on those perceptions. Here you can see a diagram that explains this. So, we gather perceptual information from the environment and then take some actions which involve interaction with the environment. Now, this loop helps us understand the environment and then interact with it in a way that we can take some actions. This is relevant because in immersive experiences also you perceive the environment as you see it through the displays, and then you take actions within that environment. So, a VR system is not merely the hardware components such as the head mounted display or computers or controllers, but it is also about the interaction that goes on in terms of tracking and the stimulation provided by the VR hardware. The hardware provides stimuli that override the senses of the user, and the VR hardware continuously tracks the user by using its own sensors. Of this, head tracking is the most important. Tracking may also involve button presses, maybe on controllers, controller movements, eye movements, or the movements of any other body parts. So, indeed there is a constant interaction going on. Even though you are attached to VR hardware, you are still present in the surrounding physical world, and there is a two-way interaction between the physical world and the organism. So, any changes to the surrounding physical world affects the organism, and the organism is still able to change the surrounding physical world in addition to being present in the display provided by the VR hardware. Consider the surrounding physical world as part of this VR system and not as aloof from the VR system. So, in spite of the stimulation provided by the VR hardware, the user will always have other senses that respond to stimuli from the real world. Okay. So, for instance, if the temperature in the room goes up, then your sweat glands will start sweating possibly, and you will experience maybe some discomfort. The user also has the ability to change her environment through body motions. So, due to your body motions, things may move, and there are things that may happen in the real world as well due to your motions. The VR hardware might also track objects other than the user, especially if interaction with them is part of the VR experience. So, occasionally the VR hardware, the virtual reality hardware, might track objects which are not the user such as a human being, and it might track objects in the room as well. And if this interaction is relevant to the VR experience, then this tracking is essential. For example, through a robotic interface, the VR hardware might also change the real world. For instance, using a robotic arm, you might be able to pick and place some objects in the real world. Under normal conditions, the brain and body parts control the configuration of sense organs such as the eyes, ears, fingertips as they receive natural stimulation from the surrounding physical world. So, when we are in the normal physical world, the physical world provides natural stimulations to our sense organs, and the stimulations are processed in our brain through neural pathways which send the stimulation signals into our brain, and based on processing of these signals, we are able to control the configuration of our sense organs. In a VR system, the VR system hijacks each sense by replacing this natural stimulation which we get from the real world with artificial stimulation that is provided by a hardware that we call a display. So, this display provides the stimulation, and to be able to provide that stimulation, this display must be generated, and for that we need a virtual world generator. So, using a computer, a virtual world generator maintains a coherent virtual world, and appropriate views of this virtual world are rendered to the display, which are then sent to the sense organs, and then all of the rest that occurs in the natural world follows. If done well, the brain is fooled into thinking that the virtual world is in fact the surrounding physical world and natural stimulation is resulting from it. So, we can create a believable world which is not a natural world, but the brain is fooled into thinking that it is the same as the real world the person is in. So, it is not the reality, but we can fool the brain into thinking that it is the reality. So, what is the mechanism at work? Well, a virtual world generator, which we can now call VWG from here on, runs on a computer and produces another world, which could be a pure simulation of a synthetic world, a recording of the real world, or a live connection to another part of the real world. So, a virtual world generator produces a new world, which could be a simulation of a synthetic world, or a recording of the real world that we live in, or a live connection to another part of the real world. So, all of these could be virtual worlds that are generated by the virtual world generator. So, a synthetic world is a world that we generate, let us say, on the computer using, let us say, 3D models, and so that consists of a pure simulation of a synthetic world. We can use 360-degree cameras or other means to record the real world, and this recording can also be played by the virtual world generator, and that will also be counted as another world. We can also have a live real time connection to another part of the real world, that will also consist of a virtual world that is generated on a computer. So, we grab images from a remote location, send it through the internet maybe, and then send it to the display on our PC, and that is then shown to the user maybe through a head mounted display. So, all of these consist of virtual worlds. So, these are types of virtual worlds that may be generated and shown on a display to a user. The human perceives the virtual world through each targeted sense organ using a display. So, we perceive it using our targeted sense organ, could be our eyes or ears, okay, and we do so through a display. So, a display emits energy that is specifically designed to mimic the type of stimulus that would appear without VR. This process of converting information from the virtual world generator into output for the display is what is known as rendering. Okay. When we convert the information from the virtual world generator into the output that is shown on a display such as a visual display or an oral display, we call that as rendering. In the case of the human eyes, the display might be a smartphone screen or the screen of a video projector as well. In the case of ears, the display may be a speaker. So, let us talk about these different types of perceptions. First, we will talk about auditory perception. It is quite important in XR. Let us understand why sound matters in immersive experiences. So, humans continuously use auditory information to understand their surroundings. We use this information that we are getting into our ears to understand the surroundings around us. So, sounds help us determine where an event is occurring, how far away it is, whether it is moving, what demands our attention, and so on and so forth. So, based on the volume, the intensity of the sound, we may be able to tell whether the event is occurring very close to us or really far off, whether that sound source is coming closer to us or moving away, whether it actually demands our attention or not. So, this is a sort of processing that we do once we hear the sound. Unlike vision, which is directional, hearing provides information from all directions. So, for vision, we know that specific object is in a certain location and that light is coming from that particular location, from that object. But for audio, the sound is coming from all directions, including outside of our field of view. So, for visual information, it is our field of view that we depend on, and what we are seeing is what we are sensing. But for audio information, we might get information from outside our field of view as well. So, audio has a key role in XR. Audio gives us spatial awareness, audio gives us guidance on whether we should pay attention or not. It gives us a sense of realism and presence, and it also helps us with safety and navigation. So, with the help of audio, we may be able to identify the location of objects and events. We may be able to direct users towards important events. We may be able to make virtual environments feel alive and believable if the audio is very well controlled. We may also be able to alert users to events occurring behind or beside them. Let us take an example. Let us say you are in a virtual hospital world on a virtual app that has been loaded onto a headset. A patient calling for assistance from the left side of the room should immediately attract the clinician's attention towards that direction. So, on hearing sounds of help, if the sound is coming from the left side, we should go towards the left, and if the sound is coming from the right side, we go towards the right. So, let us say you are clinician who hears the sound of somebody calling for help in the virtual world, then you may use your navigation controls to navigate to the left side if the sound is coming from the left side. Now, let us try to understand how do humans know where sounds come from. When a sound reaches our ear, the brain estimates its location using very subtle differences in the sound arriving at each ear. So, these differences are because the head may block some of the sound waves, the ears have different orientations and they are pointed in different directions, and the outer ear alters the incoming sound frequencies as well. The outer ear, which is also known as the pinna, it alters the incoming sound frequencies. The combined effect of these acoustic modifications is also known as the head related transfer function, or HRTF. An HRTF describes how sound from a particular location is transformed before reaching the listener's ears. So, there are various localization cues that we use. One is the interaural time difference. It is the difference in the time that a sound wave takes to reach one ear as opposed to the other. So, for instance, a sound originating from the left will reach the left ear first, and because it will reach the left ear first, we are able to tell, our brain is able to pick up this subtle clue and say the sound originated from the left. We may also be able to tell where the sound is coming from the level difference. That is known as the interaural level difference, or ILD. So, the head partially blocks the sound and the ear, which is farther from the source, receives a weaker signal. So, let us say the sound is coming from left side, my head is blocking partially the sound waves that are entering the right ear. So, that is known as the interaural level difference, that is also a key localization cue. The third cue is that of spectral cues. the shape of the outer ear modifies the frequencies differently depending on the sound direction. So, the shape of our outer ear is able to modify the frequencies depending on the direction of the sound. So, these cues let us know whether it is coming from the front or from the back or from above or below. So, here is an illustration that actually explains how this works. So, in our ear we have the cochlea module. They are responsible for monoaural processing of the sound. Once they are processed, then we make subtle calculations in our brain of interaural time difference and level difference, and our memory and other senses then process these to tell us where the sound is coming from. There are different types of aural display systems. They are typically classified into world fixed and user fixed. In a world fixed sound system, you can see a depiction here on the left. You are seated in the center and the sound sources are around you. So, there is a left surround and there is a right surround, there is a back surround left, there is a back surround right, and there are two on the left and right to your front as well. There might be one to your center as well. So, this is a world fixed where surround sound system where the speakers are fixed in the world. The other type of aural display system is where the user is fixed. So, for instance, if you put on some headphones, that is a user fixed headphone system. So, in this case on the left you could be anywhere, you could be moving, okay, and the speakers are fixed. Here the speakers move with you. So, they are fixed to the user. So, let us appreciate the differences between world fixed and user fixed displays. In the surround sound system, the generated sound or stimulus is far away from the ears. So, the speakers are far away from the ears, whereas it is quite close for the headphones. So, speakers are much removed from you as opposed to your speaker, the headphone which is on you. One implication of the difference in distance is that much less power is needed for the headphones to generate an equivalent perceived loudness level compared with distant speakers. So, power needed is much less. So, for speakers of course, we need a much higher power level because they need to traverse a distance to reach your ears, whereas with the headphones, since they are glued to your ears, they are stuck to your ears. So, you do not need much power. Another implication based on the distance is the degree of privacy allowed by the wearer of headphones. So, when you are using headphones, it is you who knows what is playing in them, but with speakers whatever you are listening to may also be heard by other people. So, surround sound system at high volume levels could for instance generate a visit by angry neighbors. So, wearing electronics on your head could be uncomfortable over long periods of time. Therefore, some people may prefer surround sound over headphones. Several people can enjoy the same experience in a surround sound system, although they cannot all sit in the optimal location. They will all be sat in different locations and there will be one location where the sound is the best. And using headphones, they would need to split the audio source across the individual headphones simultaneously if they all wanted to enjoy the same experience. The costs are different depending on the manufacturing difficulty and the available component technology. Usually headphones will be much cheaper than your surround sound system, although one can also spend a large amount of money on headphones as well. So, these sorts of differences in aural displays also carry on to other kinds of VR systems. So, an interesting thing as well, as we have been talking about, where is the sound coming from. So, let us consider when you are listening to music, you may close your eyes and imagine that you are at a live performance with the artists surrounding you. Where do you perceive these artists and their instruments to be located if you have closed your eyes at a live performance? Does it come from the stage or is it coming from some other aural displays around you? Are they surrounding you or do they seem to be in the middle of your head? If you are using headphones, it is most likely that they will be inside your head. They will seem that the sound is coming from inside your head. In a surround sound system, if recorded and displayed properly, then sound should seem to be coming from their original locations well outside of your head. They probably seem constrained, however, into the horizontal plane that you are sitting in. Now, headphones, despite offering you the privacy, do have some limitations. So, to preserve perception of where sounds are coming from, headphones should consider configurations of your ears in space to adjust their output accordingly. So, to give you a good spatial experience, the headphones should consider where your ears are in space and give you a different experience to each ear. For example, if you nod your head back and forth in a no gesture, then the sound being presented to each ear needs to be adjusted, so that the simulated sound is rotated in the opposite direction. In the surround sound system, the speaker does not follow your head and therefore, it does not need to rotate. If the speaker rotates with your head, then a counter rotation is needed to undo your head rotation, so that the sound source location is perceived to be stationary. To summarize auditory perception in XR, humans localize sound using timing and intensity differences. We talked about the interaural timing difference and the interaural level difference. Spatial audio enhances realism and situational awareness. Audio can guide attention when your visuals are overloaded, and mismatch between audio and visual cues does usually break immersion. Let us move on now to visual displays. Again, it may be world fixed or user fixed. An example of a world fixed system is the cave system, which we talked about in the last lecture, and an example of the user fixed system is a head mounted display that the 90-year-old woman is enjoying using an Oculus VR headset. Some basics of visual perception now. So, vision is the dominant sense in most XR systems. Usually, the key challenge in vision is the limited resolution and the sensitivity across the visual field. While designing vision systems, we need to think about central vision as opposed to peripheral vision. Central vision is also known as foveal vision, and we want to be keeping most of our key items in the scene in our central vision. Your design must prioritize what users actually perceive. If you do that, then you will be able to give them a good sense of presence and immersion. Talking a little bit more about foveal and peripheral vision. Foveal vision offers high acuity and it is restricted to a small central region, which is of the order of 2 degrees. Peripheral vision is sensitive to motion and you can keep low detail perception there. The design implication is that it is important information that should be placed near the user's gaze. Wherever the user is gazing at, that is where you want to be keeping the most important information. Now, how does our brain perceive depth? Well, our brain estimates depth by combining multiple cues rather than relying on a single signal. So, these cues could be binocular, monocular, motion parallax. Binocular cues come from stereopsis and convergence, eye convergence. Monocular cues come from perspective or any kind of occlusion that is occurring due to objects being in front of others, and texture gradients. Equally, whether things are closer to you or far away from you, that gives you different sound differences, and this motion parallax from your head and body movement also gives you perception of depth. So, correct depth cues are critical for giving users a sense of realism and task performance. If we think about comparison between the visual displays and the aural displays that we discussed earlier, the cave system is the analog of the surround sound system for audio displays. The VR headset is the analog of the headphones. So, cave is equivalent to surround sound and your VR is equivalent to your headphones. Now, suppose the screen in front of the user's eyes shows a fixed image in the headset. Now, if the user rotates his head, then the image will be perceived as being attached to the head. If you would like instead to perceive the image as part of a fixed world around you, then the image inside the headset must be changed to compensate as you rotate your head. So, that is what is crucial to creating a good visual display. The surrounding virtual world should be counter rotated. As such, transformations are necessary. It is a significant engineering challenge to estimate the exact amount of head and eye movement that has occurred and apply the appropriate transformation in a timely and accurate manner. And that is why it is so challenging to create a very good visual display. If this is not handled well, then users could have poor or unconvincing experiences. Besides, they could also fall prey to what is known as VR sickness. So, tracking and applying transformations becomes necessary in cave systems as well, if you want the images on the screens to be altered according to changes in the eye positions inside of the room. So, both in head mounted displays and cave systems, we need to take care of what we are displaying to the user as the user makes movements while enjoying those displays. Let us now understand the concept of dynamic viewpoint updates when it comes to visual displays. We do understand now that tracking is essential for visual displays. In immersive systems, the displayed image cannot remain static. As users move their heads, eyes or bodies, the visual scene must be updated continuously to preserve the illusion of a stable virtual world. For instance, when a user turns their head to the left, the virtual scene must shift appropriately. Objects that were previously out of view may also become visible. So, that is another thing that we may want to keep in mind. We may have to also recalculate perspective relationships, so that things appear realistic. Similarly, eye movements influence what part of the scene should receive the highest rendering quality. The key principle is that we must carry out these viewpoint updates as we sense that the user is making movements. The display image is not fixed, it is continuously transformed based on user motion. So, a number of challenges are encountered in tracking and carrying out this view transformation. We need to estimate the user motion in real time. A major engineering challenge in XR systems is to determine how much the user's head is moved, how much the eyes are moved, how quickly these movements occurred, how the displayed image should be transformed accordingly. So, system must perform these computations continuously, accurately and with extremely low latency. Now, why is this difficult? Well, that is because human head movements can be really rapid, unpredictable, it can be multi-directional and even small errors can become noticeable in immersive environments. So, tracking and visual transformation must occur almost instantaneously to maintain your immersion. If the tracking is poor, then it fails. Okay. If head and eye movements are not estimated correctly, you will have reduced presence, which means that virtual objects may appear unstable or disconnected from the environment. You may also experience visual instability, that is, the scene may jitter, drift or lag behind user movement. You may also experience reduced realism, which means that the interactions feel unnatural and unconvincing. The user may experience frustration and tasks may become difficult to perform. It can also lead to cyber sickness and VR associated sickness. User may experience different kinds of sickness such as nausea, dizziness, eye strain and headaches. So, the key observation here is that if the tracking is poor, then users feel different kinds of effects, which we must try to avoid. Often users can tolerate low graphical quality, but not poor tracking. So, tracking is crucial. Tracking is also crucial in cave systems. In a cave or automatic computer generated automatic virtual environment, users stand inside a room surrounded by projection screens. As they move, their eye positions change, their viewing angles change and perspective relationships may change. To maintain correct visual perception, the projected images must be updated continuously, rendering must account for the user's current viewpoint and the displayed scene must remain geometrically consistent. Whether you are using a head mounted display or cave, immersive experiences require accurate tracking and viewpoint dependent rendering. There are some limits to our visual perception. Human eyes have limited resolution despite high display specifications. Peripheral vision is sensitive to motion, but not the detail. Visual fatigue is often experienced by humans due to prolonged focus and the conflict between vergence and accommodation. And so, these have implications for where we place our UI and the density of our content. We have already understood the different hardware components of VR such as displays, sensors and computers. Displays generate stimuli for a targeted sense organ, where vision is a dominant sense and that is the key display that is used in most XR systems, and any display constructed for the eye must cause the desired image to be formed on our retina. For cave systems, some combination of digital projectors and mirrors is used. We have seen the architecture of cave systems in the last lecture. You may use an array of large panel displays. Alternatively, for headsets, a smartphone display can be placed close to the eyes and brought into focus using one magnifying lens for each eye. These days, screen manufacturers are currently making custom displays for VR headsets by leveraging the latest LED display technology from smartphone industry. Some are targeting one display per eye with frame rates above 90 hertz and over 2 megapixels per eye. There are displays for other sense organs that are available. Sound is displayed to the ears using classic speaker technology. There are also bone conduction methods which vibrate the skull and propagate the waves to the inner ear. This method was used in Google Glass. You also have haptic displays which provide haptic feedback in the form of vibration, pressure or temperature. Here you can see two displays. On the left is your Touch X system, Touch X. This is by 3D systems. It allows the users to feel strong resistance when poking into a virtual object with a real stylus. A robot arm provides the appropriate forces here. On the right you can see some vibrations generated by game controllers. So, these are examples of displays for other sense organs. Finally, we come to haptics and tactile perception in XR. Now, touch matters in immersive experiences, because while vision and hearing help users perceive virtual environments, touch helps them feel connected to those environments. So, haptic feedback can confirm that an interaction has occurred. It can help improve the task performance. It can increase the realism you have, because in the real world you do experience a lot of touch. It can enhance your learning and memory of tasks that you are doing within the virtual world. It can also reduce the uncertainty during manipulation tasks. For example, when we press a physical button, you see the button, you hear a click and you feel the resistance and vibration in the real world. In XR, visual and auditory cues are very easy to simulate compared to touch. So, touch remains a real challenge when it comes to XR. Touch provides confirmation of interaction and realism, and typically different types of feedback is used. For instance, vibro-tactile feedback is used using controllers. You may also have force feedback or variables that simulate resistance and weight, and these sorts of haptics usually rely on illusion rather than full realism that you get in the real world. So, we have seen various kinds of displays. We have seen oral displays, visual displays, finally, we have talked about haptics. So, brain combines information from all of these senses in our day to day world. Vision usually dominates other senses in conflicts. So, vision is usually our dominant sense, and usually we can tolerate small inconsistencies if we are transforming that into XR systems. Large inconsistencies usually cause discomfort. So, what we should aim for as designers of immersive worlds is sensory coherence. It need not be perfect. To summarize today's lecture, human perception is constructive, it is not passive. That is, the brain interprets sensory information rather than directly observing the reality. So, we are interpreting the sensory information that we are gathering from the world. Perception emerges through our continuous interaction with the world between sensing and action. XR systems attempt to replace natural sensory stimuli. So, tracking is fundamental to creating the immersion XR systems. We may use multiple depth cues for visual realism, and we also learned that successful XR design requires coherence between the sensors. We need to integrate, we need to carry out multi-sensory integration. So, as a take home message from today's lecture, we can conclude that immersive experiences are created not by displays alone, but by aligning technology with the mechanisms of human perception, and that is why it is important, so important for you to understand how human perception works. I thank you for your attention, and I look forward to seeing you in the next lecture.